the organizers for the opportunity to participate in this Gong show. As you can see, the title of my talk is Current Mean Values in the XYZ Model. But before turning to this particular model, first I would like to briefly motivate our interest in this topic, on the topic of the current operators of integrable systems, and also would like to briefly summarize some of our previous results with my supervisor Balázs Posgai and fellow PhD student Martin Borsi on this topic. So as you might know, in recent years, the transport processes of one-dimensional integrable systems attracted a lot of attention, and in 2016 in these two papers, the so-called Generalized Hydrodynamics was introduced to describe these processes in the Euler-scale. And in GHD, one assumes that the system in question can be divided into fluid cells, which are locally described by some space and time dependent equilibrium state, some local generalized Gibbs ensemble, which in return can be characterized by a root density as well. And one can derive a hydrodynamic flow equation for this root density by taking the expectation value of the continuity equation describing the conserved charges of the system. And to do this, one has to express the charge and current mean values by the root density. And this can be done by these two equations written here. Now, the first one is simple, it simply follows from the additivity of the charges. However, the second one for the currents is not so easily derived. And this form for integrable QFTs was actually proven in the original papers back in 2016. However, for lattice models, a rigorous proof was missing, and this was the main motivation for us to investigate these current operators. So to be a little bit more clear, what we are interested in is we are investigating integrable systems defined on a finite size lattice with some Hamiltonian. Because of the integrability, we know that the system possesses a macroscopical number of conserved local charges which are in involution, and they are local, so they can be written as the sum of local charge densities with a finite span. And then through the continuity equation, one can define the current operators. And the question that we are asking is, what is the mean value of these current operators in the eigenstates of the system? And in the case of the XYZ model, we answer this question in this paper. Now, because of my limited time, I won't go into the details, but we obtained a closed short formula for this current mean value using a complicated form factor expansion. But instead of going into the details, I would like to give a semi-classical picture to help understand this this formula. So we know that in the case of the XYZ model, we can construct the eigenstates of the system using the coordinate Bethe Ansatz, and it takes a form like this written here. And we can think of these states in a semi-classical picture as quasi-particles moving on a ring of size L, if we assume periodic boundary condition, with some bare velocity, which is given by their momenta. And these particles move freely as long as they are far from each other. But when they meet, they scatter on each other, and this scattering is described by the S matrix, which is just a momentum dependent phase in this case. And this scattering can be thought of as a time delay or space jump for these particles. And as a result of these time delays, the bare velocity of the particles changes, and they will acquire some effective velocity. And as it turns out, this effective velocity is just this factor in our formula. So this is really a finite size version of the current mean value formula that I showed on the first slide. So for the XYZ model, this answers the question. But then another question arises: what happens if the model does not have a U1 symmetry? Because then this semi-classical picture obviously cannot be used. And one such example of a model is the well-known XYZ model given by the well-known Hamiltonian. And this is still an integrable model, but it lacks U1 symmetry. It is an R matrix. Here, the appearance of this non-zero D factor signals the lack of U1 symmetry. This R matrix can be parameterized using elliptic theta functions. It satisfies the usual Young-Baxter equation, so it can be used to construct monodromy matrices and transfer matrices in the usual way. The transfer matrices will commute for different values of the rapidity, so it can be used to construct the conserved charges of the system. And then the question is, how can we calculate the current in this case? And to solve this problem, the first step was taken by my supervisor in this paper, where he showed that the current operators can be embedded in the usual framework of Young-Baxter integrability. He gave an algebraic construction for these currents and showed that the current mean values are actually closely related to a transfer matrix eigenvalue of an enlarged modified transfer matrix, which acts on 2 extra sites compared to the original one. Now again, I won't go into the details about this construction. What is important for us is that it can be used in the case of the XYZ model, and with this, the task to calculate current mean values reduces to calculating transfer matrix eigenvalues. And because this is an ongoing investigation of mine, I unfortunately won't be able to show the final results for the current operators or current mean values. But instead, in the remaining couple of minutes, I would like to show how one can calculate the eigenstates and eigenvalues of transfer matrices in the case of the XYZ model using a generalization of the Algebraic Bethe Ansatz, which was worked out by Takhtajan and Fayev in the 70s. So the big problem of the absence of U1 symmetry is that there is no such reference state, which is annihilated by the bottom left element of the monodromy matrix. And to solve this problem, one can apply a gauge transformation for the R matrices. And these gauge transformations take this form. They are parameterized by elliptic theta functions. They have 2 fixed parameters S and T and an integer index K. And it turns out that the transformed R matrices will have a local reference state denoted here by omega, which is annihilated by the left bottom elements of the R matrix, and also the diagonal elements of the R matrix, the action of the diagonal elements of the R matrix on this state can be calculated as well. It turns out that they will act like ladder operators on these states. Obviously, the total monodromy matrix will transform in this simple way, and using the global reference, the local reference state, we can create global reference states with the appropriate actions on these states by the monodromy matrix elements. And with this, we have a family of generating vectors for the transfer matrix. And it turns out that it is useful to consider even more general gauge transformations with general indices K and L. And then obviously the original transfer matrix is recovered if we set K equal to L, because then in the trace the 2 matrices cancel. And what is important then that the commutation relations for these monodromy matrix elements can be worked out. And it turns out that this B operator can be used to create the eigenstates of the system, just like in the usual algebraic Bethe Ansatz case. The only difference that now the number of these B operators in the eigenstates are fixed, and the number of these B operators has to be L over 2. So this construction only works if the system size is even. But then if the rapidities satisfy the usual beta type like equations, then we have the eigenstates and the eigenvalues, where here the H and alpha functions are can be explicitly written out as theta functions. And now the remaining task is to calculate the current mean values, is to modify this method to the modified and enlarged transfer matrix, which I hope that I can finish in the near future. And with this, I thank you for your attention.
Thank you very much. Let's thank Levente for the very nice talk. Are there questions?
I have a question.
Yes.
Beautiful.
Maybe I missed it, but so you discussed at the beginning you were able to calculate these mean value currents by deforming the transfer matrix eigenvalue with this epsilon parameter.
Yes.
How is this introduced? How do you deform this? Is there some constructive way of doing this?
Yeah, so this is worked out in this paper by my supervisor. So this is a nice construction. So here this J is a generating function for the currents, well, actually for the generalized currents. And in this paper, he shows that this eigenvalue, sorry, the expectation value of this generating function is equals to the modified transfer matrix, where this transfer matrix acts on two extra sides. So if the original system size is L, then this transfer matrix acts on L plus 2 sides, and on those two sides, some inhomogeneities are introduced. This mu and epsilon are some inhomogeneities on these extra two sides, and this will equal this. The claim is that this will equal to this expectation value of this J, but I'm not sure I can give a detailed explanation.
I see. Okay, thank you.
Yeah, so I have a question. Is it possible to relate it to what we considered in our papers when we take derivatives with respect to theta's? Because roughly the number of theta's are inhomogeneities of the spin chain. So roughly, I think the counting should be the same, because you also get L operators parameterized by one spectral parameter, which you can convert into two spectral parameters, I guess. So do you know if there is any relation?
I didn't really understand your question because of the noise.
Yeah, sorry, I'm in a very noisy room. Is it better? Better?
A little bit.
Can you? So I was asking whether the relation with operators which are derivatives of the transfer matrix with respect to the inhomogeneities, because number of operators at least formally looks the same as the number of currents. And for those from SOV construction, we know that it can be written in a form similar to what we have with some.
There's probably some connection to it. I'm not sure what is the concrete connection, but I would expect that somehow it is connected. But I cannot.
And then another question. So you said B is not is a bit pathological if you don't do this rotation, but in XXX spin chain you can use like any operator, A, B, C, D, any of them to create states. So is it also true for any of those, or it's all of them will have problem of the sort we discussed for B?
Yes,
because you can create states in XXX by a repetitive action of say A operator, not necessarily B.
I think so the problem is the absence of reference state, and I think that that is true for the operator, isn't it? So the problem with the XYZ case is that there is no reference state in the original case without the gauge transformation. I'm not sure I answered your question.
What does it mean? Because if you do this rotation, then you can apply this rotation to the reference state on the new frame. So it will be some state in the initial frame, which you can use as a reference state.
Oh, sorry. So then I misunderstood your question. So your question is, after that, the gauge transformation, can we generate states with other operators? That is your question?
No. My question was about this reference state. So can't you use the new reference state, rotate it back into initial frame, and then call that your reference state?
That is a good question, and actually I don't know the answer. Yeah, that is definitely an interesting question. I'm not sure about it. Sorry.
Okay.
Thank you.
Maybe
So the time is
we'll
up.
continue the discussion, during the break. And before passing to the next speaker, please let's thank Levente again. Thank you very much. Thanks.